Hello. In the previous lectures, we have discussed already the preliminaries required for studying quantum mechanics. We have studied stationary states, and in the previous lecture, we also have studied an important topic, that is the bound states. Now, the right time has come to understand our understanding of bound states from some instructive toy model. So one of the instructive model is in the in quantum mechanics initially is asymmetric infinite potential well. So today we are going to consider a one-dimensional version of asymmetric infinite potential well. So today's topic is asymmetric infinite potential well. This is the first in the topics of the instructive models or some prototype potential model, and this is very simple, so therefore we'll start our problems. We will start our potential problem from this particular case, that is asymmetric infinite potential square well. So without wasting time, let us start the lecture. So in this problem we will consider a particle of mass m. So particle of mass m is confined to move inside a potential given by Vx in one dimension. This infinitely deep asymmetric potential well is given by Vx is equals to 0 if x lies between 0 and a, and if x is greater than equal to 0, sorry, if x is greater than equal to a or x is less than equal to 0, then the potential is infinite. If this problem has to be solved, how to proceed? We already know um, we already know we've already known time independent Schrodinger equation. So we'll use the time independent Schrodinger equation to solve this particular problem. One thing one must keep in mind, that when we study classical mechanics, there is uh, there is no possibility uh, of understanding the motion of a particle where potential exceeds the total energy. This is something that we already know. So I'm going to write it here in notes. So first note that you're going to take is classically, the motion would be forbidden in a region. Motion would be forbidden in the region where your potential is, where potential is greater than the total energy. Because if potential is greater than total energy, this will lead to the negative kinetic energy, which is not possible in classical mechanics. But this kind of thing is not uh, it is not so possible in quantum mechanics. There is a possibility and probability of finding a particle in some region where Vx is greater than E. We are going to see all those cases later on, but not so possible in quantum mechanics. However, even in quantum mechanics, however, even in quantum mechanics, a particle cannot be assumed to be present, cannot be assumed to be present in a region with infinite potential. In a region with infinite potential. So therefore, uh, for the case x less than 0 or x greater than equal to a, we will consider the psi x to be 0. So psi x can be conveniently taken to be equal to 0 for all x greater than equal to 0, a greater than equal to a, and or x less than equal to 0. So for all these cases, so but we make the potential well. So let's say this is your potential well, And if you're seeing, we are considering this region, which is x less than equal to 0. And if we are taking the region x greater than equal to 0, a greater than equal to a, sorry, in both of these regions, it is convenient to assume that your psi x would be equal to 0. Because even in quantum mechanics, an infinite potential, in a region of infinite potential, particle cannot be present. So these two notes I have already written. We are going to see the qualitative part of these solutions and also the quantitative part of the solution. So therefore, as I mentioned, this is the first instructive toy model. For students, generally it is taught initially. So it is an instructive potential model that we are going to use. And this is the first of our series. And we're going to study many such different potentials. So today, we're going to pay our attention to this kind of this model. Okay. So how would we start? So as you are aware, we already know the Schrodinger equation, and we know that since the potential Vx is infinite, as I told, so for all x greater than equal to a, and for all x less than equal to 0, your psi x would be 0. But for x lying between 0 and a, for x lying between 0 and a, we know that your potential Vx is equals to what? It is equals to 0. So potential Vx is equal to 0. So here we are going to write the Schrodinger equation minus hk square upon twice m d square psi upon dx square plus Vx psi is equals to E psi. And I know that Vx is 0, so this will be equals to 2 d square psi upon dx square plus 2m upon hk square, 2me upon hk square, psi is equal to 0. So this is equivalent to solving a second order differential equation. I hope everybody knows the solution for the second order differential equation. I'll equate it to k. So this is your k square. I'll write it as k square, psi equal to 0. Here k is equal to what? Here k is equal to root over 2me upon hk square. So k is equal to what? It is equal to root over 2me upon hk square. And we know that the solutions to this differential equation, if I write the auxiliary equation, so auxiliary equation will be m square plus k square. Sorry, I'll write d square instead. So I know that auxiliary equation would be m square plus k square equal to 0, and which will give me two purely imaginary things. So I'll write this way. So the solution for such differential equations, as you're aware from the theory of differential equation, psi x would be equals to some linear combinations of e to the power iota x, and I'll write. Okay. So and effectively, if you know that e to the power iota theta can be written as cos theta plus iota sine theta, and then you can obviously convert this particular solution in form of sines and cosines, and you can simply write psi x as some, let's say write a dash b dash. You can write it as some a times sine kx plus b times cos k cos kx. Now we know that we have studied already that the wave function must be continuous, single valued, and should be single valued and continuous. So from the continuity condition, from the continuity condition of from the continuity condition of wave function psi x, it is quite clear that psi 0 must be equal to 0 and psi a must be equal to 0. If psi 0 is equal to 0, what does it mean? It means that b must be equal to 0. And what is psi a equal to 0? What this condition gives you? It gives you sine a sine ka must be equal to 0, which implies that ka must be equals to n pi. And here you can write that kn should be equals to n pi upon a. So this is your k. Now, in order to find what would be a, we'll use the normalization condition. And we know that the wave function should be normalized. So psi n star psi n dx integral from 0 to a, from 0 to a must be equals to what? Must be equals to 1. And if we use this condition for, if you use this normalization condition, um, so a mod whole square integration from 0 to a sine square n pi x upon a dx is equal to 1. So this is 1. And this integral will be equals to what? This integral will be equals to 0 to a. I can write it as 1 minus cos 2n pi x upon a dx, and then divided by 2 is equals to 1. So this is mod a whole square divided by 2. This integration would be equal to simply a, and this integration would be equal to sine. And we know that if I place a here, so this will be sine 2n pi, which is 0. If I place 0 here, 0 here, so sine 0 is 0. So nothing to worry about. So a mod whole square is equals to 2 upon a. So see, clearly this a would be equals to what? It is equals to root over 2. Okay. So now the solution. So the wave function in general can be written as root over 2 upon a sine of n pi x upon a. So this is how one can write your wave function. This is how one can write the wave function for the instructive model, the first instructive model in asymmetric infinite potential well. So where potential Vx is expressed as 0 for all x lying between 0 and a, and infinite for all x greater than n in x less than equal to 0. The wave function is given by root 2 by a sine of n pi x upon a. So this is something that one must remember. Clearly, uh, uh, correspondingly, I can also find the energy. So what will be the different energy eigenvalues? Okay, what will be the different energy values? Okay, because after all, this particular solving of differential equation uh, would result into some energy spectrum, and we want to really find what would be the possible values or permitted values of energy. So we've already know that what is Kn times A is nothing but it is equal to n pi, and we already know that Kn is nothing but it is equal to root over 2me upon h cat square. So if I use it here, so Kn square A square will be equals to what? It will be equals to n square. Then I can write pi square. And then what is Kn? So Kn square is 2me upon h cat square. This is A square, and here you have n square, here you have pi square. And from here, I can clearly write that my En, that is the energy spectrum corresponding to this asymmetric infinite potential well, will be equals to n square pi square h cat square upon twice m a square. This is how you're going to get the energy spectrum. Clearly, this energy spectrum is quantized. That is, only certain values are permitted, and it doesn't form a continuous spectrum, rather it is a discrete spectrum. Okay, so now see, any particle which is bound, here you know that your particle is confined in a limited region of space. You know that the particle m is confined in a limited region of space, and quantum mechanically the solution for this particular particle confined in a region of space that is x lying between 0 and a, this energy spectrum comes out to be discrete. That is, there will be only certain allowed values of energy, not a continuous spectrum. However, in classical physics, energy is given by p square over 2m, and it can take any value. So here the classical energy would evolve continuously, which is in sharp contrast to quantum mechanics, where a particle confined in the region from 0 to a will only be permitted certain energy values. So the particle which is confined of mass m which is confined in a region from 0 to a can only express some discrete energy values, okay, which is in contrast with the classical physics where a particle confined can have uh, will evolve continuously or will have a continuous spectrum of energy. Now, another observation. So here we'll have certain observation. So observation number one. Observation number one. If we want to find the difference between the two adjacent energy levels, that is delta En, it will be equals to En plus 1 minus of En. And certainly it will be equals to n plus 1 whole square minus n square, then pi square, h cat square upon twice ma square. This would become twice ma square. This is common, not at all an issue. So this will be equals to what? This will be equals to 2n plus 1 times pi square, h cat square upon twice ma square. So the energy between the adjacent levels turns out to be dependent upon n. And this is one thing. Certainly, since it depends upon n, so it will not be a constant. Now, for what n you are taking, so for different n, so if you are taking n equals to 1 and then n equals to 1, then this will be energy difference between E2 and E1. So this energy difference would be different from energy difference between n equals to 3 and n equals to 2. So differently, this difference between the adjacent energy will not be a constant value, will not be a constant value. This is the first observation that you can have. In fact, if you want to find what would be En delta En upon En, this will be equals to what? This will be equals to 2n plus 1 upon n square, I guess. And as n tends to infinity, this delta En upon En, this will go towards 0. So n tends to infinity means all these energy states are close to each other. That is in the classical limit. In the classical limit. Because we have seen that in classical, what is the classical position? The classical position will have energy values non-discrete. It will be having a continuous energy spectrum. You know from your standard 12th also that energy can be expressed as p square upon 2m. So it can take all the values. So it is not confined to some discrete values. But if I take n tends to infinity, that implies all these energy states are now close to each other, which implies that I'm talking of some classical limit. So in classical limit, I can write that my delta En upon En would certainly be equals to 0. Okay, so basically in classical limit, what will happen? All these energy states will become practically very close to each other and will actually not be distinguishable. Rather, they'll become indistinguishable. Okay, so I hope this is something that you should remember. Another thing, if you want, if another observation, second number observation, if you want to take, see your energy state is given by n square pi square. It's energy. You can say energy eigenvalues are coming out as n square pi square h kt square upon twice ma square. So basically what is happening, if you take n equals to 1, you'll simply get E1. What is E1? E1 is pi square h kt square upon twice ma square. So clearly your energy values for different states can be written as n square times E1. Okay, so this implies that there is an infinite sequence. So there is an infinite sequence of discrete energy levels, of discrete energy levels corresponding to this value n. Um, if I take n equals to, if I replace by n equals to minus n, you know that your psi n will remain almost the same. It will only become negative, but overall the structure wise psi n is same. So therefore we actually do not consider the solution with the negative integers. So you might have seen, because see what I did was here I wrote sine n pi x upon a. So basically Ka is equal to n pi. Here n should belong to set of integers. If even if you do sine of minus pi, that also will give you minus. Sorry, if you want to find sine minus pi, that also will give you 0. Sine of minus 2 pi would also give you 0. But the point is that there is no such difference in the except barring this sign, there is no such difference in the energy. Sorry, there is no such difference in the wave function. And in fact, the energy values are same if either if you consider E minus n or n. So therefore, we restrict ourselves to the only positive solutions. And if you take n equals to 0, then it will become quite uh, difficult to, it will give you psi equals to 0. So if you take n equals to 0, then you would simply get psi equal to 0, which is certainly a very trivial solution. And right now it is not physically acceptable. So this will give you a physically unacceptable solution. So therefore, for this bound state, that is for this particular toy model, uh, we will consider the energy, we will consider the wave function as root over 2 upon a sine n pi x over a, such that n belongs to set of natural numbers, not even 0, not even 0. We'll see what is the case. We'll see that particular case also in little detail. Uh, okay, so overall, one has to understand that that the different wave function solution for this particular problem is given by root over 2 by a sine n pi x over a, and energy eigenvalues are given by sine n square pi square hk square upon twice m a square. I hope we've already defended our position that this particular Schrodinger problem is a eigenvalue problem. So these values are sometimes also referred to as the energy eigenvalues, and these are sometimes also referred to as eigenstates. Now, another thing that one can clearly see here, that none of the state will have the same energy. Okay, so uh, so for each eigenstate, there is one energy. So I'll write it here. This is the fourth point that you should consider. The fourth point is that for each eigenstate, there is one energy level. So therefore, this, the energy spectrum, the energy spectrum for this particular potential problem, that is an infinite asymmetric potential well, is not only discrete, but also it is degenerate. Another thing that you should observe is that is that um, is this. So if you really think, if you think, what would be sine n x into psi m x, and if I take a star over here and try to integrate from 0 to a, what do I get? So even if I take star, because the because the wave function is a real wave function, so it will come out as 2 by a integration from 0 to a. This will be simply sine of m pi x upon a into sine of n pi x upon a dx. And here, if I just assimilate this 2, so I'll take 2 inside. And if you don't even remember, I also don't at times forget this formula. What is sine a sine b? 2 sine a sine b. What is 2 sine a sine b? I think it is cos of a minus b minus cos of a plus b. I hope it is right. Uh, Cos of a minus b minus cos of a plus b. So, and here, uh, just give me a minute. I'll check the formula so that I'm not writing anything wrong. So what we are trying to see, that whether our wave function is orthonormalized or not. So if it is orthonormalized, things will be quite easy to us. Although all these things we have proven in general for bound states, but still I am doing it for now specific cases. Okay, so now we are doing things for specific cases. So so this will give me 1 upon a. Integration from 0 to a. This will be cos of m minus n pi x upon a minus cos of m plus n, and then you have pi x upon a, and then you have this dx. So if you integrate this up, what you will get? You will simply get, I think there would be some constant. I'll write it here so that you don't get confused. A upon m minus n. Then you have the sine of m minus n pi x upon a minus a upon m plus n sine of m plus n pi x upon a from 0 to a. Now, if you place, and if m is not equal to 0, if m is not equal to n, if m is not equal to n, if you place a, this will become pi m minus n pi, this will be 0. If you place a here, this is a 0, 0. And if you place m equals to n, if you place what? M equals to n, then it is equal to integration 0 to a, and this will be simply sine square n pi x upon a dx, and this is certainly equals to 0 to a, and there will be some 2 by a, so 2 by a also. So 1 upon a, 1 minus cos of 2n pi x upon a dx, and this will certainly give you 1. So clearly, integral from 0 to a psi n star x psi m dx is equals to 0 if m is not equal to n, and it is equal to 1 if m is equal to n. Clearly, this implies that both the solution for the asymmetric infinite potential well psi n happens to be form an orthonormal set. They form an orthonormal set. Okay, so this is something that one must remember. And in fact, the most general solution. So if you have seen, we have so most general solution will be given by time dependent Schrodinger equation, and for that we have to multiply our solution with the time evolution operator. This will be e power minus iota ent upon h cat. So the most general solution will be equals to what? Root over 2 upon a summation n equals to 1 to infinity. This will give you sine n pi x upon a, and then you will have e की power minus iota n square pi square h cat square upon 2ma square times t. I hope it is clear. I think upon h cat also comes. So e की power iota en. So one h cat will cancel with one h cat, but overall this will be some structure. I hope it is clear. So this is one of the important topics that we have started today. A few important things that I think I have already covered 5 qualitative points. The 6th point one must remember is about the nodes. And what are the points that you should remember? What are the points that you should remember? So the first, another important point is, let me first discuss the node, and then I'll discuss another important point. So let me draw something like this. And now we'll go a little bit with right ways. Okay. So now if I make the, let's say this is x equal to 0, and this is x equal to a. Now, if I want to draw the ground state, so what would be the ground state? Ground state will be given by psi 1x, and it is equal to root over 2 upon a sine of pi x upon a. So clearly, it will reach to the maximum when x will be equals to a by 2, and then again it will go towards 0. While considering the nodes are nothing where your psi x vanishes. Nodes are those values of x where psi x vanishes. However, we are not going to take the points x equal to 0 and x equal to a. We are not going to consider these points. At these point also the psi x vanishes, but we are not going to consider them as nodes. So this is your the ground state. I'll write here ground state. And you see clearly the number of nodes. So I will write nodes by, let's say, capital N. So number of nodes will be equals to clearly 0. And this is the maximum point. So here it attains the maximum point at a by 2. So at x equal to a by 2, you know that the ground state will have a maximum of psi. So I'm just writing it here somewhere. This is equals, this particular thing is equals to, I'll write it here. X is equal to a by 2. I hope it is clear. Okay. Now, if you consider the first excited state, the first excited state would correspond to n equals to 2. So psi 2x will be equals to what? It will be equals to root over 2 by a sine of 2 pi x upon a. Okay. Now clearly at a x equal to a by 2, this will become 0. And at x equal to a by 4, just think about it. A by 4, it will reach some maximum. So it will reach some maximum. At x equal to a by 2, it will cut. And at x equal to 3a by 4, again it will come down. And then here. Okay. So this is the this is the first excited state. Number of nodes here happens to be 1. So just remember, if I'm placing n equal to 0, the nodes are n equal to 1, the nodes are n equal to 1. If n is equal to 2, then the number of nodes capital N is equal to 1. Now let me consider the third state. So if I take a third state that is corresponding to n equal to 3, I want to say. Obviously, this is the second energy, second excited state. So I'll write second excited state. Okay, so third excited state will be 2 over a sine of 3 pi x upon a. So now at a is equal x equal to a by 6. Okay, so this will get a maximum at x equal to a by 6. Okay, at x equal to a by 4. So a by 4, what will happen? At a by 4, it will be equal to sine of 3 pi by 4. And okay, so I'll have to, how will I make? Okay, so this is something, I'm drawing it again. So just give me a little bit of space I need. Okay, so I'll write it here. So that, see, at x equal to a by 6, psi 3x will be equals to what? And if I write x equal to a by 6, what will be psi 3x? It will be equals to root over 2 by a sine of pi upon 2. So this will be equal to simply root over 2 upon a. Okay. When it will become, so now x equal to a upon 3, psi 3, a by 3 would simply become 0. Now at x equals to, further if I go, if I do something like this, a by 3 plus a by 6, so this will become 6 and this will become 2. So basically at x equal to a by 2, psi 3 a by 2 will be what? Just think about it. Psi 3 a by 2 will be equals to what? It will be equals to root over 2 upon a sine of 3 pi upon a into a by 2. So a cancels, 3 by 2 is minus. So this will give you negative of root over 2 upon a. So it will give you negative of root over 2 upon a. Is that fine? Okay. So having said all these things, so how will the graph look like? So it will peak at what? It will peak at a by 6. Then at a by 3 somewhere, this is a by 4, I think. So a by 3 will lie somewhere here. So basically now it will come down somewhere. At x equal to a by 2, it is having a negative value. So I'll write it here. Then again, you see here, and then again you see here. So I hope this is a kind of figure you will get for the second excited state. So for second excited state, you are clearly seeing that there are how many number of nodes? There are 2 nodes. So if I take any small n equals to 3, then the number of nodes which I have represented by capital N equals to 2 uh, is equals, the number of nodes which I have denoted by capital N comes out to be 2. Okay. Uh, Let me try, if there is certain sense of patience left with you, then I can also make what you can say for the third excited state. So we are going to draw psi nx for the third excited state. So third excited state, how will it look like? So for third excited state, that is psi for x, it will be equals to root over 2 upon a sine of 4 pi x upon a. So clearly, I'll make small things so that this was, I think, a upon 3, I think. So what would be a upon 4? Somewhere here. And what would be a upon 8? Somewhere here. I think I'm not making it to scale, don't worry, but just making it somehow. So a upon 4 here. So at a upon 8, it will peak. So it will peak at a upon 8. At a upon 4, again it will come down. So it will come down certainly. Then after that, a upon 2. So if I take a upon 2, it will, I'll have to make this thing this way. So a upon 8 plus a upon 4. So what it will be equals to 8 here, and a plus. So what will be 3a upon 8? So if I take x equal to 3a upon 8, what it will be? So psi 4 at 3a upon 8 would be simply root over 2 upon a sine of 4 pi into 3a upon 8, and then you'll have a. So, a cancels a, and this will become this 2. So 3 pi by 2. So this will become minus. So if I take 3a upon it, so it will come as negative here. And then again, what will happen at x equal to a by 2? So at x equal to a upon 2, a cancels. So sine would come out as, sine will come out as 0, I think, here, not that part. Just think about it. Just think about it. I want to really make it to the perfection. So see, a upon 8 is fine. I'm making it again. So at a upon 8, what would be psi 4 at a upon 8? Psi 4 at a upon 8 will be simply root over 2 upon a sine of 4 pi a upon 8, and this is a. So a cancels a. So sine, it will give you root over 2 upon a. Simple. Now at a upon 4. So if I take a upon 4, what it will give me? It will give me root over 2 upon a sine of 4 pi into a upon 4. So this will give you simply sine pi, which is certainly 0. So I have given 0. Now if I take psi 4, 3a upon 8, 3a upon 8. Okay. So if I take sine a, 3 sine 4, 3a upon 8, it will give me what? It will simply give me 0. It will simply give me minus of root over 2 upon. Is that fine or not fine? I hope it is clear till now. I hope it is clear till now. So it will give me a negative of root over 2 upon 8. So at 3a upon 8, it will be, I have made it on the negative side. Okay, I have made it on the negative side. Now, instead, if I take a upon 2, what will happen? Just think about it. Just think about it. What will happen if I take x is equal to a upon 2? Okay. So if I take x is equal to a upon 2, what will happen? I'm writing it here. Psi 4 at a by 2 will be equals to root over 2 upon a sine of 4 pi, and here it is a upon 2. A will come, a will cancel. This will 2 sine 2 pi simply 0. So it will be 0 here. So I'll have to make it in thoda sa right way. Just give me a minute. Okay. So now we are going to make it in a nicer way. Actually, this was a little bit messy here. Okay. Now I'll make it here this way. Okay. So this is your I'm not making it to complete perfection. Like I'm not trying to uh, make in the same way as above, but just think that let's say this was somewhere a upon 3, so somewhere a upon 8 will be here. Let's say, and in fact a upon 8 would be all the modes this side, but just not making to the scale, just making it to give you a qualitative idea. A upon 4 will be down, 3a upon 8 will be here somewhere, a upon 2 will be again 0, so I'm going to make it 0 here. Just give me a minute. Okay, so how it look like, how will it look like? Just let me make it in the right way, otherwise you won't be able to get what I am trying to make. Okay, so sorry, so this will be this way. Okay, so it starts from here, I think. At a upon 8, it will peak. At a upon 4, which will be, I think, median of it. So I'll make a little bit this way. And then it should return back to 0 here. And then again, it will start from here, and then all those calculations same. So you can see that here the number of nodes are what? 1, 2, 3. So n equals to number of nodes, which is capital N equal capital N, that will be equals to 3, and this I'm making for n equals to 4. So the third excited state, where which corresponds to value n equals to 4, the number of nodes come out to be 3. So clearly, for the general energy general wave function, that is psi n, the energy eigenvalue will be equals to what? It will be equals to n square pi square h cat square upon twice ma square. And this particular eigenstate will have n minus 1 modes. It will have what? N minus 1 modes. So you can clearly see if n equal to 4, then the number of nodes was 3. If n is equal to 3, then the number of nodes were 2. If n equals to 2, then number of nodes were 1. And if n equals to 1, then number of nodes would be 0. So this is a relation that you should remember. In fact, another thing that you might have observed here, that there is a certain sense of symmetry. Okay, so here you can see that there is an asymmetry. That is, this is a reflection, a mirror reflection kind of thing here. Here it is completely symmetric. Again, this is symmetric here. So whatever, if you take at x equal to a by 2, just consider x equal to a by 2. This is symmetric about x equal to a by 2. Then this is again asymmetric about x equal to a by 2. This is again symmetric about a by 2. This particular plot, you can clearly see this is asymmetric about a by 2, about x equal to a by 2. So this is another observation. I'm just writing it here, that the solutions are solutions to solutions. You can write the energy, eigenstates. Eigenstates are alternatively symmetric and asymmetric about x equal to a by 2, that is the midpoint. Alternatively symmetric about, alternatively symmetric and asymmetric about, antisymmetric about x equal to a by 2, that is the midpoint. And lately you're going to find that this sense of symmetry is no unique thing. We've already seen if the potential is symmetric, then the wave function would be either even or odd. This is something that we have already studied in the previous lectures. However, our system is not symmetric as such, but obviously we can make our system symmetric. So for example, if I see here it is x equal to lying between 0 and a, I can obviously make it symmetric. Okay, I can obviously make it symmetric. All these things you have studied, I've already proven this particular thing, that if potential is a symmetric potential, then wave function would be either even or odd. Okay, so either even or either odd. So here, this particular sense of symmetry, is not so unique. We've already seen. But however, you can think that, okay, the potential clearly doesn't seem to be symmetric. However, we can make it. However, we can make it by slightly shifting it. So all these things, however, doesn't make that amount of sense, but just doing it for this little bit of your understanding. If I shift my potential well from x equal to 0 to a to minus a by 2 to plus a by 2, now clearly this potential well is symmetric about x equal to 0. We'll discuss all these cases uh, lately also, and we'll prove that the bound state of such symmetric potential are either even or odd. So basically, this proves, initially we have already proven it in a very general sense for the bound state. We'll prove it for very specific potential where Vx would be equals to 0 for x lying between minus a by 2 plus a by 2. These bound state would either have an even parity or odd parity. We are just not considering it right now. And I was just telling you something, so I told you something. I told you this particular thing. We'll do it in a greater detail later on. But understand that the solution, the sign, which is the root over 2 over a sine of n pi x upon a, they're alternatively symmetric and anti-symmetric about x equal to a pi. Okay. Another thing that you have to understand is completeness. Now, if you want to write any wave function of a particle in an infinite, in an asymmetric infinite deep potential well, then you can always write it in terms of, or as a linear combination of various eigenstates. This you can do. And if you're solving a time dependent problem, then obviously you have to multiply with the time evolution operator. Okay, so this solves this particular thing. From here, we've covered one of the aspect of one-dimensional potential well. I'll do a problem today and let you know what is one another tip that I want to give. So already there are 6 to 7 notes, qualitative notes that I've already given. 8th note is about problem solving. So whenever you get a problem, always remember to write the always try to write the wave function psi x in terms of the eigenstates. Always try to write psi x, that is the wave function, in form of the eigenstates. Then your problem will become slightly easy. Otherwise, you will struggle with the problem. So, 8th qualitative point I wanted to make was for the problem solving part. I hope till now everything is clear. Now let us do a problem, and then we'll be able to understand what I wanted to say with the last point. So probably the last point I'm going to explain this way. So let's say I'm considering a particle of mass m, which moves in a one-dimensional region x lying between 0 to a. So I'm considering a particle of mass m moving in a region from x equal to 0 to a at t equal to 0. At initial time t equal to 0, the wave function is given by root over 8 upon 5a 1 plus cos pi x upon a times sine pi x upon a. So if this is given to you, so what I'll do, I'll simply, then we want to find first, the first thing that we really want to find is at any later time, let's say t naught, how would the wave function look like, or what would be the wave function? So we really want to understand how would the wave function look like at certain different time t equals to t naught. Okay, so I know I will have to solve the problem. I know that, okay, so I know this is, uh, so mass m is confined. I'm writing mass m, particle of mass m is confined in this region at time t equal to 0. The wave function is given by this. And okay, so basically this is the problem. So the particle is confined between x equal to 0 to a. So clearly this is a problem of asymmetric. This is a problem of asymmetric infinite potential well. So this is a problem of asymmetric infinite potential well, which we have already studied. And we know that what are the eigen states corresponding to this? The eigenstate corresponding to this is root over 2 upon a sine of n pi x upon a. So the last advice that I gave you, I'm going to use that. I told you, whenever problem comes to you, always try to write sine x in term of eigenstate, because we know that this psi x form a complete set of solutions. So this is complete. In completeness, what we want to, we've already have seen in postulates and other previous discussion, what does completeness mean? That I can write psi x as a linear combination of the various eigenstates. So the psi x, so I'll write it here. So point number one, what would be psi x at time t equal to 0? So I'll try to write it in root over 2 upon a. So this will give me uh, the first thing, I think I'll write it here. So this is root over 2 upon a sine of pi x upon a. Whatever extra is there, I'll write it here. So I'll write root over 4 upon 5 here. Okay, so this is first thing. Then plus this particular fellow. So I'll write 2 here. If I multiply with 2 here and divide by 2 here, so this will give me, I'll write it here. So I'll solve it here somewhere so that you can understand what I'm doing. Root over 8 upon 5a is given to you. So what you will do, just write this 8 as 2 root 2. And then this sine of pi x upon a into cos of pi x upon a. And this will particular fellow with 2 would become what? It will become root over 2 upon 5a, and this will become sine of 2 pi x upon a. So this will become root over 2 upon and this particular thing root over 2 upon a, sorry, this particular thing root over 2 upon a, and then uh, this will become 1 upon root over 5. So I'll write somewhere here times 1 upon root over 5 sine of 2 pi x. So I hope you are getting it, what I want to convey, that whenever question comes, try to write your wave function in form of the eigenstates. This is root over 2, 4 upon 5, and this is nothing but it is equal to psi 1 plus 1 upon root over 5. This is simply psi 2. This and this. Okay, so this is your psi 1. So your wave function can be written as root over 2, 4 upon 5 psi 1 and root over 1 upon root 5 psi 2. If somebody says what would be the wave function at any later time t equals to t naught, so you know what you have to do. You have to multiply this particular expression with the time evolution operator. So here it will be e to the power minus iota e1t upon h cat. Okay, and here it will be plus 1 upon root over 5, 1 upon root over 5 psi 2 e to the power minus iota e2 t upon h. So at any later time t equal to t naught, so I have written t naught. Okay, so I hope it is clear till now. Okay. So this is how you can write. If you want to express it or all the more in a rigorous way, then it will be psi of x comma t naught will be simply equals to what is psi 1? Psi 1 is root over 2 upon a. So it will again become root over 8 upon 5a exponential of minus iota pi square h ket square upon twice m a square, and this h ket cancels, h ket only here, and then this t naught, and then simply sine pi x upon a, and then this will be simply 1 upon root over 5, and then you have root over 2 upon a, so this will become this, and this will become root over 2 upon a, and this will be sine of 2 pi x upon a, and exponential minus iota 4 pi square h upon 2m a square t. I hope it is clear. And then you can obviously take something common out and do write things in this fashion. Then I can do something like this. I can simply write root over 8 upon 5a, and then I can take things common out, and then simply it will be like this, e to the power minus iota pi h ket t naught upon 2m a square plus. So I think this is simply, if I've taken 8 common out, so this will become 1 upon 2, and this 2 pi x upon e. So I'll simply write it as exponential minus iota 2 pi square h ket upon ma square, and this t naught, and then 1 upon 2. So this will become simply cos of pi x upon a, this whole multiplied by sine. I hope this is something that you can verify on your own, I think. Okay, so this is simply mathematics and nothing else. So overall, wave function at any later time t naught is given by this huge expression. I have written it in the form of the question only. Okay. Now, what will be the average energy of the system, or the expectation value of the energy? So what is the average value of the energy? You can say what is the average value of the energy of the system. What is the average value of the energy of the system? So you know that corresponding to the energy, you know that the operator is simply h ket. So this is how you're going to get the, and I know that wave function is already normalized, so this will become 1 only. So I know this will be simply what? This will be simply, uh, this will be equal to simply, what is your psi? Psi is simply, and you know that h ket psi is simply en psi. You know that h ket psi is simply en psi. And what is psi? Psi is already, you know that it is root over 4 upon 5 psi 1 plus 1 upon root over 5 psi 2. So this is your psi. I hope this is something that you already know. So clearly, the energy, average value of energy at time t equal to 0 will be equal to what? It will be simply equals to this h ket psi. And you know that psi 1 and psi 2 are orthogonal to each other. Are all orthogonal to each other. So what you will get, we'll simply get this equals to 4 upon 5. So just square it up. This will be 4 upon 5 E1 plus 1 over 5, sorry, E2. Because psi 1 and psi 2 are orthonormal to each other. So I hope this is something that you know. Okay. Psi 1 and psi 2 are orthogonal to each other. So clearly psi 1 star, psi 2, this integration from 0 to a dx will become 0. So you're left with only this thing, psi 1 star psi 1 dx. So this will give you psi 1 mod whole square. And because this is h ket, this is what? This is h ket psi. So h ket psi, if I do an h ket here, so what I will get? I will simply get E1. This will be what? It will be E1 psi. And I know that psi 1 mod whole square would be 1. So this will, you will get E1 only here. So you will get only E1. But the point is this, with psi 1, you are having root over 4 upon 5. This will also accompany root over 4 upon 5. So overall, it will become 4 upon 5 E1 plus 1 upon 5 E2. So the average value of the energy would be equals to 4 upon 5. What is even? Even is pi square hk square upon twice ma square. And what is E2? E2 is, I think, 4 pi square hk square upon twice ma square. So this will give you in totality 4 upon 5, 4 upon 5. So this will give you simply 4 upon 5 again. So this is 4 upon 5 pi square hk square upon ma square. So the average value of energy would be this. And in fact, even at time t equals to t naught, if you want to find, at time t equals to t naught also, if you want to find, the average value of energy would remain the same. Because you see, at t equal to t naught, what will happen? This psi, I'm writing this psi, would be equal to what? It would be equal to root over 4 upon 5 at time t equal to t naught. This will be psi 1, sorry, psi 1, and this will be accompanied by exponential, and this is, understand, this is the bra vector. So you will have, instead of minus iota, it will be plus iota. Plus root over 1 upon 5 psi 2, and then exponential iota e2t upon hk. And what is hk psi? So hk psi will be equal to what? It will be simply root over 4 upon 5 even psi and exponential minus iota even t upon hk, and then plus root over 1 upon 5 e2 psi 2, and then you'll have exponential minus iota e2t upon hk. Okay, and you already know that psi 1 and psi 2 are orthogonal to each other, so they will become 0, and you are left with again, and this particular thing, e ki power iota even t upon hk, and this is e ki power minus iota even t upon hk. So both of these terms, when multiplied, would become 1, and you are left with root over 4 upon 5 whole square even psi 1 psi 1, and then another term would be root over 1 upon root over 5 whole square. This will be psi 2, psi 2, and then this will be E2. So clearly you know that this will become 1, this will become 1. So you will get simply 4 upon 5 E1 plus 1 upon 5 E2. So even if you're trying to evaluate the average value of energy at a later time, then also the value would remain the same. That is, it will give you the answer as total average value of the energy will be 4. I think this is pi square hk square upon 5 ma square, if I'm not wrong. Now the next question that arises is about what is the probability of finding the particle on the left side of the box. So what is the, just think about it, and this is something that I, what is the probability of finding the particle on the left side of the box? On the left side of the box, that is, left side means that is x lying between 0 to a by 2 at any later time t equals to t naught. So for that, you already know that how to find the probability of finding the particle at any later time. So it gives you, so basically the probability is given by 0 to a by 2 psi star psi dx. And in fact, this is being evaluated at what? This is being evaluated at time t equals to t naught. So I'll write t naught here. This is psi star and psi at x comma t naught dx. So this will be equal to what? Integration from 0 to a by 2 modulus psi at x comma t naught mod whole square, and then this is dx. So this particular probability of finding the particle between 0 to a by 2, it turns out to be 0 to a by 2, and this entire thing, psi psi x comma t naught mod whole square, this particular thing you evaluate. I think this can be evaluated on your own end. And this, I'm writing it here. It will come out as sine square uh, pi x upon a. This is not a problem. Then you will have 1 plus cos square pi x upon a plus 2 cos pi x upon a cos 3 pi square h cat t naught upon 2 m a square. And this entire thing is time dependent, so you don't have to integrate with respect. You have to integrate with respect to x. You have to integrate this only. So this is one, and this probability turns out to be dependent upon time t naught, and this turns out to be 1 upon 2, 16 upon 15 pi cos 3 pi square h cat t naught upon 2m a square. Because I'm running late, so therefore I've just written the solution, direct solution. You try to find out this integration on your own end. It's very easy. It's not a big deal. You know that you have to integrate from 0 to a by 2 sine square pi x upon a. You can write sine square theta as 1 minus cos 2 theta upon 2. Then again, sine square cos square, you can write this sine square cos square divide into multiply by 4, divide by 4. You can write it as 1 upon 4 sine square 2 theta. And then sine square 2 theta can be written as 1 minus cos square, 1 minus cos 4 theta. So all those things I hope you can do on your own. So therefore, I've just written the direct answer. I hope you've been benefited by this lecture. Please let me know in the comment section what else needs to be improved. In the next session also, we are going to do some questions with regards to the one-dimensional infinite asymmetric potential well. Till then, take care. Bye-bye.